The only manner in which we've had a little trouble, like I mentioned earlier with GPUs, some of the call routing ability would be greatly enhanced by the ability to parallelize some of the code. So what we've talked about in the future is to extend some of the convolution into the
basically
GPU.
right now the software is kind of a mismatch for the hardware resources we have available. So in the future, that's one of the next steps we kind of outlined in the report was to take better use of all of those resources. And given enough time and money and other resources, we need to be able to do that. The key was to get something functional.
Absolutely. So what we have running currently is the ability to call internally in our network, and we can actually show that to you if you'd like to see. If you guys want to initiate a call. What you see here is the back end. This displays some of the call statistics. This is our machine interface. This is accessible through the same network we use to get outside to the real world. And you can see the call coming in.
So there's just some status updates here. It's basically, it'll say it's initiated the call, it's ringing, it's waiting for the answer, and it just kind of delineates each of those steps until the call has been connected, at which point
you're welcome to listen if you'd like.
Between the two phones, where is the signal going?
The signal goes to the radio in the back.
So we have it pushed
gets
back
processed
a
and
ways.
routed back out to the cell phones. We're broadcasting at relatively low power to comply with the law.
Sounds good.
If you guys would like to listen, you're welcome to. Say hi.
Hi.
Good. Hey, how are you?
I'm pretty good.
Live demo.
Live demos are
If you notice any choppiness standing this far back, it's because we targeted
Low power.
And I don't
Low
hear
power.
too many of the other people around us, so that's very good. Good call calling. You'll notice a
Thank you very much.
bit of a time delay.
Yeah, there was some delay.
Say hi.
All cell phone calls have time delay, but you don't notice that.
No, you're
because
not
never
seeing it. You
standing in
can't see
front of
the
the
face.
person. Exactly.
Yeah, his lips were moving before
I can hear you. Can you hear me?
got the signal.
So you'll notice some latency.
Oh yeah, well, I expect.
Yes, of course.
We'll start to go.
In a normal cell phone system, you wouldn't notice the latency as much because you'd be in different rooms. Absolutely. Are there questions we can answer for you about the project?
Well, you still have some time.
Oh, we do? Then we can tell you about a couple other things.
Yeah, they'll
about
give you a
that.
2-minute
Sure.
warning.
We're all electrical engineers, undergraduates, and one of the things we wanted to take on in this project was to venture into a little bit of mechanical engineering, and so Damaris has put together a case for us using SolidWorks, really excellent design. This is actually designed to hold the development boards, but if we were to integrate it into a single unit, we would just shrink it right down and bring it in there. This shows the exploded version of the case.
Yeah, we tried to encompass kind of all the facades that we would need to actually have a working product and be able to present it to people to possibly get venture capital or move forward in taking some of our design innovations and actually putting them into one box on our own custom hardware.
I can also talk a little bit more about the measurements we've done on the system. That was one of the particular challenges of our design, evaluating it. The resources necessary to do full evaluation on RF is quite expensive. So what we've done, first we focused on system resource usage as a function of calling. You'll notice there are slightly different axes here. The network resources usage is quite low. But we looked at RAM, USB, network, and CPU usage as a function of number of calls, up to the 2 units we have available. We also looked at call quality and signal strength. Call quality, we just assigned a subjective scale ranking from not clear to semi-clear to clear to very clear, which actually showed strong correlation to the signal strength data. We, again, to comply with the law, we can't broadcast very far. We did spec it to, I think, 30 meters.
30 meters
Indoors?
Indoors.
outside a wall, so the transceiver is in the room and you're in another room. So 100 feet in a room like this, that's about the range we got. And outdoors, about 70 feet. And
There's greater noise outside. Actually, the original idea for the project was simply because in one of those rooms we have no cell phone service. We have a basement lab, and we were hoping to pinpoint target that to provide service.
the metric we used was was a conversation. If we can maintain a conversation, that's what we cut off.
In the future, we're hoping to be able to look into more intense measurements. We actually do have an RF lab on campus that we've been talking to about speccing the antennas. I'd also like to send some broadband noise through the system to see the frequency effects from one end to the other, as well as, more importantly, how calls drop off in different frequency bands as a function of time, distance from the units.
And I think one of the other big things that kind of is like an undertone to the whole project is the documentation that we made. So we ran into a lot of issues developing it as far as getting kind of partial documentation and not really knowing how to configure it exactly. So we would build the system up and then strip it all down again and just use the documentation that we had created to see if we could duplicate it. Because I mean, an open source project is no good if it's not replicatable, if you can't replicate it. So we really hammered on the documentation and kind of feeding back to the open source community, so that if someone else were to attempt this, that kind of would be a thing they could leverage.
We've all really benefited from the open source community. A lot of our work is based on work in forums, as well as some of what has turned out to be a little bit sparse documentation. And so what we're hoping to do with this project is to bring it back into the community. Like I said, the software that we're using to interpret GSM, as well as to handle some of the call routing, is a little bit spotty documentation, and we would love to show back to the community kind of the same love we've received.
In our report, we gave an overview of some of the steps required in the Linux world to gather and compile and put together and properly configure the software needed to incorporate both the Edis transceiver as well as CentOS and other things on the Intel Atom itself.
Also, in terms of future development, we would really like to bring some of the functionality of the Edis box, the software-defined radio, into an environment like the DE2i. What's running inside the Edis box is Cyclone 2. It's the baby brother of the Cyclone 4. The only difference being some amount of RF front end. And so if we would be capable of engineering something like that, or there are available boards from TI that we could plug directly into the HSMC ports, which would allow us access. We decided, like I said early on, to change directions a little bit, but that is one of the...
We made a fairly decisive engineering decision about halfway through the project to not incorporate the RF front end onto the FPGA on the board. We simply didn't have enough time.
Yeah.
We got the hardware, and we came to the realization that in order for us to have a working product when we were to come here and our other needs for this project and in our education process, that we needed to have a working product, and we made a pretty harsh and quick decision that this is the direction we're going to go.
Absolutely.
And we just pursued the Edis. But the likelihood of being able to actually implement that transceiving hardware software package on here is pretty high. We did the back end research. However, the physical work and the coding work required was bigger than us at the time.
Also, in terms of future work, we're definitely looking into extending into the modern technologies, 3G and 4G LTE. Some of that is a restriction of the open package we're using. So I suppose we're out of time, because I just want to thank you for your time and letting us present.
Now it's Q&A time.
Now it's Q&A.
Yes.
Do you have questions for us?
Put like the GPS button on my GPS.
We don't. I can do a song
My
and dance.
question involves how many of these units would you then need to install?
Sure.
Because these slightly populated are usually way spread apart, right?
Sure. So a normal cell phone system with large towers are quite far apart, and each one covers a large distance and a large number of consumers. And ours is scalable depending on the amplification you place on the RF front end. So we could potentially, and of course the processing power, as well as, like I mentioned, the optimization.
There's also a current dilemma that we face, that the construction of cellular phone towers can't sustain the market right now. That we're going to run out of churches and high-rise buildings to place cell phone towers on.
As well as bandwidth.
Yeah. So another potential use case, it's not our targeted challenge, but another potential use case is telephone poles instead of towers, to where you can actually mount these devices down the street on a telephone pole and give coverage to an entire neighborhood without putting a giant tower up and trying to paint it like a tree.
The short answer to your question is it depends on the use case. We could conceivably use it in a single room in our basement lab to extend coverage, assuming the providers would be willing to provide service through a network interface into your house. We also could use it more densely distributed to cover a neighborhood or farther apart, provided sufficient communication.
Yeah, that was going to be my question. I mean, the cell phone only answers to one master.
Yes.
So you need a cooperative
Absolutely.
service provider in order to do
Yeah, oh
this,
yes,
right?
oh yes.
So, okay, I just wondered if you had done any, research, with an AT&T, Verizon, Vodafone.
We talked about doing
any of
that.
those guys.
What you're describing is, I think it's kind of two-pronged, because on one hand, like you're saying, if they were to cooperate, it's a piece of cake, so to speak. The other part of it is, if you have a bunch of these kind of, if you can imagine the Wi-Fi route, what happened with Wi-Fi routers, there's maybe dozens of different vendors, and they need to be able to cooperate so they're not stepping on each other's toes if they are doing this. So this kind of what they call self-organizing networks is like a really big research topic that is kind of a whole layer on top of just the hardware itself. Right?
I have a
Currently,
follow-up question.
oh yes, please.
So with regards to your assumption of a WAN or a LAN at the back end, in the countries that are, I'll just say, ill-served, how are you getting that? How's your backbone working? How are you overcoming the fact
That's
that
an excellent question.
the whole world isn't wired?
Right.
China, for one, is not
absolutely.
wired at all.
Yeah.
So that comes
Right?
down for us to a question of scope.
Okay.
Our goal was to address it after that question ends. Assuming you can get some data in there, our goal was to provide service that was designed in a way that would help communities organized in sparsely or in small units. So similarly, if you brought in a large tower, you'd still need the trunk line, but you'd have inefficient coverage. You'd have these large $150,000 towers to cover small communities or very sparsely distributed communities. So our scope ends at getting the service there.
So then one more follow-up.
Sure, absolutely.
So what do you think the capacity ultimately will be given the computing resources that you have? How many handsets?
This is an interesting question.
I
So,
talked about this.
so it depends on the computer resources. We have been able to successfully make no more than 2 calls given the current software configuration, which is small, obviously. Do you have numbers actually on how on the
way that
convolution?
GSM, because this is all GSM, so there's CDMA and there's Verizon's a whole different thing. Basically, every channel that you broadcast on, you get 7 simultaneous sessions. We can only do 1 channel, and we're only able to get 2 of the 7. So the real towers, you see the rectangular antennas that kind of they array them around. Those are probably broadcasting on maybe 5 or 10 different channels simultaneously. So you multiply that by 7, and then by the number of arrays. You can scale it really well. We don't know how that would fit in this, to be honest with you, because we did this resource usage, and we found, well, we're hitting it at 2, and it's software. And what happens after that? Maybe that graph completely inverts. We're not really sure.
Yeah, and that's why I was asking, is the effectiveness of open source, right? I was really getting at your take on the effectiveness of open source versus, what the TEMs actually do, right? Like a Cisco, like a guy like an Ericsson, for instance. Right, that's their bread and butter.
Yes.
Right, they love that open source performs like this, and so I was interested in your answer about, well, how did you go about the performance issue?
Yeah, I think the direct answer is it's something we'd like to investigate more, but it's a lot of work. As you could probably realize to do that.
Do you know what the biggest pain point is? Is it just the RF front end?
It looks like right now it's CPU because it's doing a software routine that's pinning the processor at 2 calls.
Particularly, it's a convolution routine, which, like I mentioned, is parallelizable. So we could very likely bring that into a GPU and see a drastic reduction in CPU overhead.
What about just threading and we're talking like 4 threads that help you?
Tried to use the math kernel library convolution routine, and it just died. And that was like maybe a week or a month before. I think that was about a month ago, and I was like, okay, we can't do it. So we'll let that.
But
be
that's
for
definitely
now.
looking forward. Also, to address your question of coverage, it also comes back to the distribution of the nodes. One method of covering more users is simply to add more units. But again, that comes down to a cost issue. So at some point it becomes too expensive to solve. What other questions can we answer for you? I'd be happy to tell you more.
Right. Yeah. And so is it just basically
The role of the computer itself is
This is SSH
monitoring?
into the Linux system running here, just for monitoring.
Yeah, there's a web server running on the DE2 along with the whole cell phone system, and we just kind of use this as a view into it to configure it, to monitor it. and it's the goal is to make it a little bit more user friendly by providing something that's graphical as opposed to purely terminal.
So does that use some
It does.
resources?
Some of the resources.
If you take that off, can you make another call?
To be honest, all the testing was actually done without the web server.
Oh, without. Okay.
So we don't know if that would actually even worsen the situation, but it seems to be pretty negligible by comparison.
Yeah, from experience, it's not a tremendous amount of resource usage. And this can be hooked up, sitting next to it like this, or over the network, over the internet.
Alright, time's up.
Oh, well then we'll end, and I'll say thank you very much. We really
Thank you
appreciate
guys.
it.
Thank you. Nice logo. I like that.
Oh, thank you very much.
Very
That was professional looking.
That was
Yeah,
Chris.
that's good. Very creative.
Very good at what he does.